Yeah, thank you all. I'm really happy to be here, and thanks for putting this talk together. It's really fun to see all the work going on here. Yeah, it was cool to see the Julia talk. That this will be kind of similar, but really what I'm going to focus on is what are the things I had to add to Egglog in this case to make it usable from the Python ecosystem. And particularly, what are the ways that those can drive further theoretical development, in this case in Egglog and more broadly with eGraphs. So that's the general kind of case here, is that there's an opportunity to make an impact in large real-world communities and in turn also help drive the theory. So this is just like a little visual of how I was kind of thinking about the work. In this talk, I'm going to be looking at the pink and the blue lines, and kind of how I'm thinking about it is you have people writing Python code. It's imperative to some degree, and then you want to move this to a functional world of Egglog, and then you want to probably move it back to Python to have this kind of loop, like Zach was talking about, going, how do you get things actually out? So in this talk, we'll go through some kind of techniques that developed to do this in a systematic way, with the goal to build composable kind of domain-specific languages in Python. And there's more in this notebook, so I won't go through everything in the talk, but it'll be there if you want to look later. So to drive this use case, to drive kind of this process, I'm gonna look at a particular use case of, let's say I'm a data scientist and I have some classification I'm trying to do over some maybe larger amount of data, and I'm using a scikit-learn, a common API in Python, to do a classification. And I want to make it faster, right? But I don't want to rewrite my code. I just want to make it faster. So to skip to kind of the end, we can make it quite a bit faster, but relying on eGraphs and also heavily relying on Numba, which is an optimizer in Python. So this talk will go through all the techniques I needed to add to kind of get to this place. That makes sense. So the first thing, if we want to optimize this sort of a function here, is we have to run it abstractly. So instead of running it on a concrete array here, like I have some array that I made of NumPy arrays of real numbers, I instead want to run it on an abstract array. So I can make two abstract arrays, and I can make some assumptions about them, like their shape and their d-type, and then I can run this original scikit-learn function passing in those arrays. And so this will just work with Python, and because they act like arrays, what I get out is a symbolic array. We'll get more into why we need these assumptions, but this is the representation of what we get out. It's quite large, and obviously wouldn't expect anyone to read it, but the point is that it's basically just a bunch of math of all the operations that scikit-learn was doing under the hood in a functional form. And so this we'll use this later on. But the first technique that comes up here is you might notice that all of these values, for example, are wrapped. So like here I'm multiplying not just by a Python float, but I'm multiplying by a scalar NumPy ND array. So to implement this kind of conversion, we had to implement this in the library, and so this shows up like in the scikit-learn, where here we're dividing by a float. So Egglog, for example, doesn't know how to divide by a float, right? It knows how to have abstract functions. And so we kind of upcast this float into this ND array scalar with a float value. And so I had to add this logic for implementing conversions in Egglog. And so it basically works as a graph of types, and you can specify from type A to B. There's a way to upcast, and it'll find the lowest cost path from the argument you pass in to the type that's required. So this allows you to use your Egglog objects just like you would Python objects, and not have to wrap all your arguments. So there's a longer example here that you can look at if you're interested. So that's kind of like how you get things into Egglog. But then another question is, how do we get them out, right? So in scikit-learn, for example, when it's running this function, you'll see that it actually has to do some things eagerly, right? It's not all just a big functional program, right? Or in Python, we have imperative code, so this is an if statement. So how do we evaluate this if statement if we don't know the actual values of these arrays? Well, below here, this is the kind of functional form of what it's evaluating. So we have our assumptions here about the arrays, and we want to know whether we need to renormalize based on this this Boolean value. And actually, using some sign analysis, we can evaluate this without knowing the values of the arrays, just based on our assumptions. So this is something else we had to build in, is how do you actually, so at certain points, like if, for example, here, when we call bool, this is in Python, when you turn into an actual Boolean, like in an if statement, we want to run a little mini egraph, saturate it, and evaluate it, and we must get back an actual value, right? So this is a place where we need to get something out of the egraph. So that's something we had to add. So this is kind of like how you go in, how you come out. And then the next is Python is imperative in other ways, right? It has mutations. So in this case, we're setting a value of an array. We're avoiding division by 0. So this is in the scikit-learn code again. It's replacing all zeros with ones. And so we had to support this. How do we, if we have functional objects, how do we support mutation? And the way that we kind of do it is by treating the mutation just like we turn it into a functional operation. So there's a little graph here that might help, but like here we have the set item operator, which is what is being used here, that mutates, right, the array. So instead of mutating the array, it'll return a new array that is the mutated version, but it will act like it'll mutate this container here in Python. So basically you can treat it like you would a Python object, and if users are using mutations, it'll all just work out, but in the egraph, they'll be functional, and you can write rewrites on them in a functional way without any state. So another piece that we kind of need in the egraph is subsumption. So this was needed because here I talked about Numba. So Numba is a compiler for Python, and it doesn't support all of Python. So not all of NumPy. So for example, here it doesn't support mean with this access parameter. It only supports sum. So we need to do a rewrite from mean to sum, but sum here is larger, right? This will be a larger cost. So how do we tell Egglog, hey, don't extract out this larger version? In this case, we want to use the larger one, not the smaller one, even though it has bigger cost. So we added this function to Egglog called subsumption, so you can pass this into a rewrite, and it'll mean that once the rewrite is run, the left-hand side, in this case the mean, cannot be extracted and it can no longer be matched. So it kind of adds some linearity to the process and allows us to run these rewrites and extract out these larger terms. So saying in this particular case, maybe usually we want to leave this mean, but in this case we're using Numba, so we want to translate it to a sum. So we can see we can simplify our original expression with these number rules and other simplifications. We get a slightly smaller expression. We won't look at it carefully, but you'll see here there are actually some means here that needed to be translated. So this is all well and good, but this like large expression, obviously it doesn't really, what are we going to do with this? So this is like where we come to sort of the other way to get programs out of Egglog. So one way was like, hey, we want an actual value, like a Boolean or an integer. We can do that eagerly, but what if we want a sort of an abstract representation of a program? Well, really, what we want to do is compile it to something like this. So this is a Python function, right, that has each operator in the graph shows up here, and it's deduplicated, and it's all ordered properly, and you'll see there's some imperative code here as well. So how do we go from this to this? So this was sort of some rewrites that I worked on in Egglog, and it's all functional rewriting, and there's basically a way to create programs and statements, and it does sort of a top-down traversal of the tree and then a bottom-up traversal, and it makes sure that every program has only one and only one parent. So it does some kind of tricks using some of the the features of Egglog that gives you some more expressivity, so that when we compile it, it's ordered basically. So this was like another piece where, hey, this is kind of feeding back into the theoretical research of how do we actually, take a functional program and create an imperative one inside of an eGraph. This I just remembered because of Zach's question earlier about taking things in and out. I actually also added Python objects inside the eGraph themselves. So if you want to do rerating on those, that's possible. Just like another primitive, like an int or a string, you can actually store Python objects in the eGraph and use them in rules. So those were a quick overview of some of the things I had to add to make this work in this use case. Some future work, which I'm very excited about, and thank you, Sue, from who works on Numba, for providing this example, is working on functions as values in the eGraph, and hopefully generic types as well. And so to help kind of drive this work, you might have a user write this sort of loop nest code, and you want to use some rewrites to convert this high-level API into a lower-level one, and then compile this to Python. So I won't get into the details, but that's kind of some future work. And overall, I guess the message is that, that I think the Python ecosystem is a great place to be experimenting here, because there's a lot of work that's data intensive, and so there's a way to do the trade-off where it's worth the extra time to do the compilation. So there's kind of a chance to have a big impact and also obviously influence the theory. So if you're looking for playing with eGraphs or building DSLs in Python, feel free to try out this library and ask any questions. Thank you.